Hello! We are excited to announce the release of version 4.4.0 of HELYX and ELEMENTS, the open source CFD solutions of Aegis. In this video, I'm going to walk you through the latest features and improvements included in this version. So, let's dive in. In version 4.4.0, we addressed the recent request from our customers in the AEC industry, which is the ability to import native Rhino 3D surface files directly into HELYX and ELEMENTS. This functionality is now available through the graphical user interface under Geometry Import. The split surface function, commonly used to divide surfaces for applying boundary conditions or to apply specific mesh settings to a surface, has been enhanced in this version. You can now choose between manual and automatic modes. When using the automatic option, surfaces are split based on feature angles, which significantly simplifies the process, especially when working with complex geometries that require multiple splits. We have also introduced a small but helpful improvement when adding primitive shapes, like boxes, cylinders, and others. These shapes can now be automatically fitted to the size of the visible geometry. While simple, this feature is especially useful when using primitive shapes for volumetric mesh refinement. Starting with a shape that's already close to the intended size makes the setup process faster and more efficient. When creating a mesh in HELYX and ELEMENTS, the first thing you need to do is to create an hexahedral background mesh, and then all subsequent refinement applied to volume regions or surfaces will be relative to this background mesh size. The background mesh is defined under base mesh, and previously only isotropic background meshes were available. In version 4.4.0, we added the ability to generate anisotropic background meshes, where you have the flexibility to define either the cell edge length or the number of elements in each direction. This new anisotropic option can be very beneficial for simulations involving, for example, thin geometrical features, or directional flow gradients, or boundary layer dominated physics. Still talking about the background mesh, in this version we have introduced a new option for defining a cylindrical base mesh, also known as an all-grid mesh. This mesh type is especially beneficial when working with axisymmetric geometries, such as rotors, impellers, or similar rotating components. It provides a more natural and efficient way to capture the flow features around these shapes. Another improvement made in this version regarding the mesh generation process was the ability to smooth the boundary layer cells between patches with two different first cell height values. So let me show you a simple example for a better understanding. When defining the boundary layers at walls, the user can specify the first cell height in meters for each surface boundary. If two attached boundaries have two different first cell height values, there might be discontinuities in the flow solution because of such jump in the cell size near the wall. In this case, the wall in the left-hand side has a first cell height of 5 cm, while the adjacent wall in the top has a first cell height of 5 mm, 10 times smaller. As we can see, the transition is not very smooth along these boundaries. Therefore, in this version, we have added a new option called First Cell Height Smoothing Iterations under the Layers settings. Please note that this option is only available for the extrude algorithm. This option controls the number of smoothing iterations applied to the first cell height in the near wall layers. If I turn this option on and generate the mesh again, the resultant mesh presents a much smoother transition along these boundaries, which is numerically beneficial for your simulation. We have also improved overall meshing performance in version 4.4.0 with between 5 and 10% faster meshing times when using features such as proximity refinement and feature snapping. We also introduced performance improvements when generating the mesh in single precision. Gains of around 10% in speed and memory usage were achieved, like in the Niigata benchmark case from AIJ as shown in the screen. And finally, a new capability has been added to HELYX and ELEMENTS graphical user interface, the ability to create 2D meshes. First, you select the 3D geometry to be used as base, click on the 3D to 2D feature on the top ribbon under the Geometry tab, and set up the plane to extract the 2D geometry from the base 3D geometry. This creates a 2D ribbon geometry in the XY plane that now can be added in surfaces under the Mesh tab. Then you apply the mesh settings as usual, such as boundary layers, mesh refinements, and the background mesh size. After clicking on Create Mesh, the result is a native 2D mesh, as you can see in the screen. In terms of setup, we have expanded the capabilities of the convective heat transfer boundary condition at walls to support more advanced thermal modeling. Previously, users could define a fixed heat transfer coefficient and a fixed ambient temperature to represent interaction with the external environment. With this update, it's now possible to specify or map these values directly from a point cloud profile, allowing spatial variation of ambient temperature and heat transfer coefficient across the boundary. This enhancement enables a much more streamlined and realistic workflow, especially when working with experimental data or results from another CFD simulation. We have also improved the performance of simulations using MRF by optimizing how MRF fluxes are calculated, especially when using multiple rotating zones, like a vehicle with multiple or 4 car wheels. We have achieved 5 to 15% faster simulation times. We have improved the thermal source term used to simulate heat conduction in rotating solids by now supporting arbitrarily shaped bodies, and not only perfectly symmetrical ones as in previous versions. With this update, heat can now flow around holes and obstructions, and this is especially useful for applications such as brake cooling systems. While this approach doesn't fully replicate the accuracy of a simulation with a dynamically rotating mesh, it offers a highly practical and efficient alternative when modeling this type of application. In version 4.4.0, we have added thermal runaway modeling capabilities in HELYX and ELEMENTS core, enabling simulation of battery thermal management under critical conditions. This new model introduces a temperature-activated heat source, allowing users to replicate runaway behavior in battery systems. Please note that this feature is only currently available via the core interface, with graphical user interface integration planned for a future release. We have introduced the new thermal source to model radiation and convection through porous materials. This allows heat exchange between the porous solid and the surrounding fluid, acting as a thermal shield. You can specify the solid's density, thermal capacity, heat transfer coefficient, and radiation emissivity, enabling more realistic simulations of materials like insulation foams, heat shields, or brake linings. In earlier versions, we introduced the vector function that could dynamically activate or deactivate cell zone regions while applying a thermal source, ideal for simulating localized heating effects. With version 4.4.0, this functionality is now fully supported in the graphical user interface, making it easier to configure and manage without editing dictionary files manually. In version 4.4.0, we have added support for reacting flows in both HELYX and ELEMENTS core, significantly expanding the solver's multi-physics capabilities. This includes features like buoyancy-driven flows, multi-region conjugate heat transfer, multiple combustion models, surface film modeling, Lagrangian particle tracking, and even pyrolysis. These additions open the door to advanced thermal and reactive simulations, such as fire modeling, engine combustion, and thermal degradation. Reacting flow support is currently available only in the core, with graphical user interface integration planned for a future release. We have expanded support for cavitation modeling by adding new models alongside the existing capabilities. The following cavitation models are now available: Schneider-Sauer, Kunz, and Merkel. This gives users greater flexibility when simulating liquid-vapor phase change, especially in turbomachinery, marine, or hydraulic applications. I particularly loved this next tool that was added in this version, which is the Statistical Convergence Assessment. This tool automatically judges convergence in simulations by using statistical data, and this is how it works. It works by first filtering out initial transients from the signal, followed by the use of confidence intervals and trend line analysis to judge whether the monitored value, like drag or volumetric average, has stabilized to a statistically significant degree. Crucially, autocorrelation correction is used to enable the application of these statistical methods to time series data. The overall method presents several novel features that allow simulations to be reliably terminated automatically once the signal is adjudged to be converged. This not only ensures that you don't run simulations for longer than is strictly necessary, but it also guarantees that the measured mean value consistently achieves a predefined accuracy. In terms of performance, we have significantly optimized the performance of the single precision solver, achieving between 20 and 40% faster computation times for both steady-state and transient simulations when compared to the double precision solver. For example, in a test using the Engis Formula 1 test car model, the simulation ran about 30% faster, while delivering nearly identical drag and lift coefficients. In this version 4.4.0, we have extended the charting functionality by allowing you to define algebraic expressions directly in y-axis charts. You can now create custom plots by combining variables through mathematical expressions, and the new calculator tool makes it easy to select variables and build those expressions visually. We have improved the split layout and multi-display options in the graphical user interface, making it easier to work with multiple views at once. A new link camera option lets you synchronize camera positions across displays, perfect for side-by-side comparisons or analyzing different variables from the same angle. If you have used HELYX or Elements before, you are likely familiar with the runtime visualization tool. To use it, you first create a set of predefined scenes in which you want to generate images from, and select the frequency that you want these images to be saved during runtime. This is great since you don't need to store full result fields, making it perfect for analyzing transient behavior with a nice frame rate without filling up your disk. In version 4.4.0, we have focused on reducing the computational overhead of this feature. Using our Formula 1 test car as a benchmark, we saw up to 26% reduction in simulation cost when using runtime visualization, depending on the mesh size. This makes it even more efficient to track simulation progress visually, reducing performance compromise. One of the export options of the runtime visualization tool is the EDF format. To visualize such new type of images, you should use our EDF viewer, which comes included within HELYX installation directory. Unlike regular images, EDF files store actual field data in each pixel, allowing you to adjust the scale, switch fields, or even compare results between two simulations, all from a single image. Finally, in terms of our additional modules, we have enhanced the stability of the pressure-based coupled solver, especially when capturing transonic flow features. These improvements were validated across a variety of high-speed turbomachinery cases. HELYX adjoint can be combined with HELYX coupled, enabling significantly faster and more stable convergence of adjoint sensitivity fields. We have also improved the underlying numerical schemes, making the adjoint solver more accurate, reliable, and consistent than in previous versions. In HELYX Marine, we have enhanced the 6DOF motion library to support self-propulsion simulations using actuator disks, improving realism in propulsor modeling. We have also introduced a rigid body deformation boundary that works with both regular and irregular wave conditions, enabling more advanced interaction between floating bodies and wave environments. So, those were some of the new features and enhancements included in version 4.4.0. Our customers can already download HELYX and Elements version 4.4.0 in our customer portal under Downloads. We also encourage you to check our new online documentation under the Documentation section, which provides a much more friendly interface to navigate through our QE and Core Users Guide. And if you're not a customer but want to learn more about how our open source CFD solutions can enable the full potential of CFD at your organization, feel free to contact us at our website or reach out to anyone from Engis on LinkedIn. We are all passionate for CFD and certainly we would love to discuss about your CFD challenges. I hope you enjoyed this new version of HELYX and Elements, and I see you in the next release.